Today we are going to talk about influential points and departures from linearity. So the first thing I want to talk about is what they're going to do on the AP exam to kind of avoid the issue of you incorrectly typing data into your calculator. Rather than you type in like 50 data values and then run linear regression and realize you typed in 100 instead of 10 and everything is wrong, they will most likely give you what you see on the screen. It will be a computer output. And this computer output gives you everything that you need for a linear regression. So the first thing I'm going to point out is the main thing. So remember, for a linear regression, we are trying to predict y based on a y-intercept and a slope. And so A typically references the y-intercept, B typically references the slope. And so what we kind of pay attention to first is on the left-hand side of this computer output, typically they're going to list the slope and the y-intercept. So for the y-intercept, it typically is titled intercept, y-intercept, y-int, constant. It'll be something in that nature of a phrase. The other part, the slope, is going to come in for whatever your x variable you are talking about is going to be. So in this case, our x variable for this particular computer output is age. So I will be plugging in age and getting out a response variable. So it may say age, it may say hours, it may say number of homes or something along those lines, but they will have something indicating what the x variable is. Now, underneath that, you should typically see the standard deviation of residuals. And this is one of those things where if they don't ask about it, you don't talk about it. Now, just to kind of highlight what that means for this particular situation, standard deviation of residuals is going to be the approximate size of a typical prediction error. So what that means essentially is this number that I get tells me what my average error is. So normally in this case, I'm off by about 0.97. So we spend a lot of time with this in Unit 9, but just for now, knowing what it is so that you don't use it incorrectly is kind of the big part we want to take away from Unit 2 and all of our 2 variable data. Now, the next thing is our r squared, which we have talked about. That's going to be our coefficient of determination. And so that tells me, we talked about how it's basically like a grade. So if I have a high r squared value like I do right now, that's telling me that about 95% of the y values that I have can be explained by the linear relationship with x. So that means they kind of fit to what the line is predicting. Now, one thing about the coefficient of determination, r squared and r have a direct relationship. So if I know r squared, I can find r by just going in and taking the square root of that number, which we'll do in just a second. Now, having all of these pieces, I can create the least squares regression line. So I'm going to go in. I don't really know what this data set is predicting, so I'm going to go ahead and just call it y hat for now. I'm going to put in my constant, my y-intercept of 3.371. I'm going to put in my slope of 2.1143 and my x value of age. Now that I have my linear regression made, I can go ahead and go in and find my r value. So I'm going to come in. Now remember, in order to find r, we just have to take the square root of r squared. So I'm going to take the square root of 0.954, and let's see what we get for that. 0.954. Let me drag it a little bit so it's not so big. Okay, so I'm going to go second square root 0.954. The big thing here is you have to remember it has to be written as a decimal when you go in to take the square root. So my R value is going to be 0.98. Now, remember, one thing about this is R tells you two things. It tells you strength and it tells you direction. So in this case, because it's really close to 1, we can say that it's strong. Now, the thing about this that you have to be careful about, if I'm getting R from R squared, I have no way of knowing what the original R value was, because if I take a negative and I square it and I take a positive and I square it, it's both going to generate the same number. So what you have to pay attention to is the slope. So if I go in and I look at the slope, it's 0.21143, which is positive. So that means the direction of this relationship is going to be positive. If my slope was negative, I would say it's negative. Now, influential points. So we're going to go in and we're going to see what the linear regression would be for this particular set of data with all of the points included. And then we're going to take out a point that we consider to be influential and see how it changes our slope and our y-intercept. So I'm going to go in and I'm going to show you my linear regression. Let me switch over. Okay, so I have my data, stat, edit, in L1 and L2. So I went ahead and typed all of the X values into L1, all of the Y values into L2, and I'm going to run my linear regression by going to stat, calc, all the way down to option 8. And then it's just going to ask me what data do I have, and then where do I want to store the regression. Remember, if you want to store it, you can always do alpha trace and then tell your calculator to store it in Y1, for instance. And so this is going to give me my linear regression. So I have y hat is equal to 0.93 plus 0.97 x, because that is my slope and my y-intercept. Now, in this case, the R value is pretty moderate at 0.77. Remember, the closer, or 7.8, let's round it to 7.8. The closer we get to 1, the stronger it is. Now, if I wanted to see this graph on the scatter plot, I would go to second y equals. I would make sure my plot 1 is on. Let me make sure, where am I? There we go. I'm going to make sure my plot 1 is on. Hit enter. And then I'm going to turn mine just to be a little bit easier to see. And then I'm going to hit zoom 9. And then I have my points. And you should see that on the scatter plot on your paper. Now, this is the linear regression with all of the data included. Now, they want us to go in and look at this data as if the 0.25 is an outlier. So I'm going to take that 25 point out of my data. So I'm going to go stat, edit. I'm going to go to 2, delete, 5, delete. And then I'm going to repeat the process. Stat, calc, linear regression, same thing. I'm actually going to store this one in Y2 just so that we can see it compared to what we have originally. And so this least squares regression line is going to be y hat is equal to negative 0.47 plus 1.23 x. And my R value jumped all the way up to 0.91. So it went from a moderate relationship to a strong relationship. And if we look at this graph, zoom 9, oh, I didn't, there it goes. We can see that the line itself has changed. So now it has a lower y-intercept and it has a steeper slope. So we're going to go ahead and we're going to kind of explain what that means for each of these summary kind of statistics. So what happened to the slope? We can say the slope increased because the 0.25 was influential and pulled the LSRL towards it. And then what happened to the y-intercept? The y-intercept decreased. Due to the slope increasing. And what happened to the correlation and why the correlation increased? Because the remaining points had a closer spread around the line of best fit. So because those points fit the new linear regression model a lot better, that caused the correlation to increase. So that kind of wraps up our talks on influential points. Remember, it's again one of those things where if they don't bring it up, I wouldn't bring it up. But if they ask you, is a point influential, you're trying to determine, is it going to change my correlation and is it going to change my slope, which in turn usually will change your y-intercept. Now, let's talk about some departures from linearity. Now, normally, the best way we can kind of talk about data in stats is if it's modeled by a line. Now, a lot of the data that we encounter doesn't always fit that criteria. However, we can transform data in a way that it can be. So a lot of this is going to look like things that you saw in Algebra 2, just to kind of show you a really quick rundown of what that can be. On the very last page of your notes, there's a table that talks about the different types of transformations we can do for data. So one of them would be taking the ln of x and the ln of y, natural log. One would just be taking the natural log of y, the square root of x, and potentially the ln of x. And a lot of this is kind of different approaches to making curved data, like what you see, straight. And the nice thing about what we've seen on the AP exam is they don't make you decide on your own. They tell you what they want you to do, and you just kind of have to follow through with what they've done or what they're telling you to do. So let's go in. We are going to actually do a natural log transformation because it can kind of be applied in any situation. I am fairly certain you know that a square undoes a square root. So natural log is the one where a lot of people mess up. So let's go ahead and open our calculators. I'm going to go ahead and put my data into L3 and L4 just because I already have it typed in. So stat, edit, and you should see I have the hours in L3 and the numbers in L4. You can absolutely keep them in L1 and L2, and it's not going to make a huge difference. Just when I change my numbers, you won't change yours. So I'm going to go and create a scatter plot. The first thing I'm going to do is I'm going to clear out both of the equations I used in the last problem because your calculator will still try to graph those if you asked it to do Zoom 9. Then I'm going to go to second y equals. I'm going to make sure that all of my settings are right. I will have to change this to say L3. Let me delete L3 and L4. If you have not changed it, you don't have to. And then I'm going to hit Zoom 9. And so I'm going to get a scatter plot. So I'm going to sketch it out really quick. This is going to be hours. And this is number of bacteria in thousands. So I'm just going to put number of bacteria. And it appears that for the most part, 3, 4, 5, 6, 7, 8, 9, I have a curved scatter plot. which again is not great because I can't do any of those things that I would normally do for linear data, where I talk about the y-intercept and talk about the slope and how things increase and decrease. So we will eventually change this. But if you wanted to create a residual plot, the first thing that I want you to kind of make note of is you must run linear regression first. Otherwise, your calculator will not run the correct line because it's just going to use whatever the last thing you ran a linear regression on is. That's all it knows. So you have to tell it what the predicted line is in order for it to do the residual. So I'm going to go in and do stat, calc, linear regression. I'm going to change mine because, again, I just have mine in a different place. If you don't have to change it. L4, delete, L3, and then I'm going to hit enter. I'm not even going to write this down because I really don't need it at this point, but I am going to go in and I'm going to now graph the residual plot. So back to second y equals, and instead of having my y list be L4, in your case, instead of it being L2, we're going to change this to be the residual list. So the way we do that is we have to go to second, stat, and then if you look all the way down at number 7, you should see something that says residual. Sometimes it's 8, sometimes it's 9. It depends on how many lists you have going. So I'm going to hit resid, and that's what we want to be set up. So I'm going to make a little note, y list. We want it to say resid, and we get that by going to second stat, and then typically, again, it's number 7. So now that I have that, I'm going to hit zoom 9. Oops. Delete zoom 9. And you should see the residual plot. Now, one thing about residual plots is in order for them to be a good fit, you want to see no pattern in your residual plot, and you want it to have random scatter. And what I'm looking at with the residuals on the y-axis and the hours on the x-axis, I'm seeing a very clear curvature in the residual plot, which is not good. So I'm going to go ahead and say, why is the linear model not appropriate? So one thing that you have to make sure is that you reference what you're looking at. So the scatter plot shows a curvature, and the residual plot shows no random scatter. So the linear model, oops, flip it back. Linear model is not appropriate. Okay, now what we can do is we can transform this data. And so this particular graph happens to look like an exponential model. And the best way to undo exponents in an equation, or exponentials, is to go in and take the log. So they're going to ask us to take the natural log of every single number that we have. So we have x, we have y. They want us to take the natural log of y. So that's our transformation. So I'm going to go to stat. I'm going to go to edit. And in L5, if you go all the way up to the very top and you hit LN and you tell your calculator, I want you to run this data from L4 and take the natural log of it, it's going to generate all of those numbers for you. So now my data is actually in L3 and L5. So second, y equals, I'm just going to go in and switch this back to L5, second 5, and then I'm going to hit zoom 9. And here is my new scatter plot. So if I'm doing hours versus number of bacteria, I'm going to have to keep not turning that. Number of bacteria, I have a 3, 4, 5, 6, 7, 8, 9, a pretty straight set of data. And so this is data that I can go in and talk about slope and talk about y-intercept, which is why we kind of do this. So let's go in and let's find the residual plot. So the first step is always to run your linear regression. So stat calc 8. And then I'm going to make sure I change these. So this should be L3. And this should be L5. And then I'm going to go ahead and fill in my next part just so I don't have to keep going back and forth. So this is going to be the ln of bacteria, because that's my y value, and its predicted y, so I'm going to give it a little hat, is equal to the y-intercept from my calculator is negative. If you have zeros, I always go to at least the first digit. So I'm going to go 0, 0, 5 plus 0.58 or 59, sorry, 59x, which is hours. Now remember, you can always write x and y out to the side. You just have to make sure that you identify what each variable is before you use it. So now let's go in and find the residual plot. Second y equals, I'm going to go to y list, delete what's there, second stat, and number 7, and it should be the residual plot. Zoom 9. And what you should be looking at is a plot. Should look something like this. Hours on the x-axis, resid on the y. And you should see a fairly random bit of data where there's no real curvature forming, which is what we're looking at. So this means that the model is a good fit. Oh, I put my equation in the wrong space. Let's just drag and drop. Sorry. This is my linear regression. I'll make it smaller. There we go. ln of bacteria. So why is this a better model? So we're going to basically reverse what we said in the other statement. We're going to say the scatter plot appears to be linear. And the residual plot shows random scatter. So the linear model is appropriate. There we go. Okay. Now, using the equation above, what would be the predicted quantity of bacteria after 3.75 hours? So I'm just going to take what we have, ln bacteria is equal to negative 0.005 plus 0.59. And where hours is, I'm going to plug in 3.75. And let's see what we get. So negative 0.005 plus 0.59, 3.75. So I'm going to have this is equal to 2.2075. And the best way to get rid of a ln is to use a base e, because e and ln are going to cancel each other out. So I'm going to have my predicted number of bacteria is going to be second divide, let me get my e, to the power of 2.2075. So 9.09. Now, the one thing you have to be careful of is this was in thousands. So I actually have 9,090 bacteria. And the last page we kind of already discussed. That is just going to show you different transformations that you could possibly see. But again, if they have a question like this, they're going to tell you what they want you to do. So make sure if you see things like square root, you're squaring your data before you're done. Or ln, you're taking it to the base e before you're done. So just pay attention to the transformations that they give you.